Hello, everyone. My name is Zhongduo Zhang. I am a PhD student from the University of Notre Dame, and my topic today is the application of SUBGRID numerical model on storm surge and tsunami inundation in a coastal urban area. The research project is in collaboration with the Disaster Prevention Research Institute of Kyoto University, Kansai University, and Japan National Port and Airport Research Institute. Here are some backgrounds for our study. Tsunamis are posing threats to some of the highly populated coastal cities around the world, especially in countries like Japan. In 2011, the Tohoku earthquake and tsunami caused significant damages to multiple coastal cities in northeastern Japan, such as Kesenuma and Sendai, leading to more than 10,000 casualties. There is also a highly concerned tsunami possibility related to the Nankai Trough megathrust earthquake, which puts a large portion of Japanese coastal industrial area in danger. On the other hand, storm surges are a much more common issue for the coastal cities. Most notably, the 2005 Hurricane Katrina was a lingering disaster for the city of New Orleans. And recently, the 2018 Typhoon number 21 Jebi made landfall on the Osaka area, inundating the Kansai International Airport, one of the busiest airports in Japan. With the increased coastal flooding events in recent years, it is in need to develop a reliable model to forecast the inundation in coastal cities. For the numerical models studying the tsunami and storm surge inundations, traditionally there are two different branches. The first one is low resolution and symbol forecasts, using a coarse grid for the topography input. The accuracy of the low-resolution models can be low, but they are easier to run as they require less computational resources and generate results in a relatively short period of time. On the other hand, there are also high-resolution simulations using finer grids, which can provide results with much higher accuracy. But those models usually run on large parallel computing systems and may take several days. An intermediate approach is the SUBGRID model. Through an averaging process of high-resolution surface elevation into coarser grids, the SUBGRID model can achieve higher accuracy with less computational time and resources. Our research goal for this study is to study the behavior of tsunami and storm surge inundation in a coastal urban area through a physical experiment, and to explore the possibility of applying the SUBGRID numerical model on complicated urban settings based on our results from the physical experiment. The physical experiment of our study was conducted in Japan. The wave basin we used for the experiment is the hybrid tsunami open flume in Ujigawa Laboratory of Kyoto University. The flume is 20.5 meters long, 4 meters wide, and 2 meters deep. The design water depth for the experiment is 0.877 meters. A city model was set up on the right side of the flume on a platform which is approximately 0.877 meters high, and there was a 1 to 10 slope connecting the city model to the bottom of the basin. The city model we used in the experiment was a 1 to 250 scale model of a real city in Japan, Kainan Wakayama, located south of the Osaka area, where tsunami and typhoon storm surge are projected to have a big impact to this industrial city, with multiple refineries and oil tanks, as well as dense population. The model also reflects the vertical elevation of the city. To record the inundation around the city model during our physical experiment, 12 wave gauges in total were used. Wave gauge 1 was located about 12 meters offshore the city, right near the wave maker to record the initial generated waves. The other 11 gauges were located inside the city model, whose locations are marked on this figure with the topography of the model. 4 of the gauges, wave gauge 2, 3, 6, and 9, were located inside the water, and the others are on land. Wave gauge 4 and 7 were near a large building north side of the port. Wave gauge 10 and 11 were located on both sides of a railway station. And wave gauge 8 and 12 were surrounded by a dense region of the residential buildings. We mainly use 3 different types of test cases in the experiment. There are constant flow cases, which produces a flow with constant flow rate from the wavemaker, representing the storm surge conditions. Mainly 3 different flow cases were used. There are 0.025, 0.035, and 0.08 cubic meter per second. Each test case lasts 5 minutes long. There are also Nankai scenario cases where the prediction of the Nankai trough earthquake tsunamis were used. To counter the scale-down effect of the CD model, we also amplify the original predicted tsunami waves by a square root of 2. Each test case for the Nankai scenario lasts 12 minutes. We also conducted several solitary wave cases with wave heights of 0.05 and 0.06 meters. But these solitary wave cases last 2 minutes long. For our subgrid model, our topography input was obtained by LIDAR scanning of the CT model. The resolution of the topography is 5 millimeters. The figure shows a part of the model input. The scanned CT model lies from x equals to 0 to 8 meters shown in this figure. And remaining sections of structures and bathymetry on the left side were manually added as they are simple enough and do not really require the LIDAR scanning. A deep reservoir was also added on the right to represent the actual situation where all water flows into the reservoir on the right end of the wave flume during the experiment. And here is a simple summary of the governing equations of our subgrid model. The model uses a grid averaged conservative shallow water equation. The model inputs a high resolution topography and generates a coarser subgrid through grid averaging process, which takes the wet and dry conditions of each area in the original topography into account, so that having a higher accuracy than simply using a low resolution grid. The figure on the right side is an example of a 5 centimeter subgrid averaged from the 5 millimeter topography. The model takes care of the averaging process and runs on the coarser grid. And due to the time limitations, I cannot show all our results from the model, but here I want to show several of them. The results shown here are a constant flow case with a flow rate of 0.025 cubic meter per second. 2 different subgrid resolutions were used, the 5 centimeter subgrid and the 1 centimeter subgrid. The original resolution was 5 millimeters. Wave gauge 1 represents the initial input, and wave gauge 2 and 3 in the water show a pretty good match with the experimental data. However, a large difference in the model and the experiment results, around 1 centimeters, can be seen for the wave gauge 4 on land, where model results have larger inundation than the experiment case, and coarser subgrid has larger inundation than the finer one. The same tendency can also be observed for the land gauges elsewhere. The wave gauge 5 has a better result, but wave gauge 7 and 8 have large difference. It is notable that both wave gauge 4 and 7 are located on both sides of a large portside building, and wave gauge 8 is located in a high building density area. And here are the results of the rest of the gauges. Overall, the comparison between the model results and experiment data of the constant flow cases potentially indicates that the accuracy of the subgrid model may be related to the existence of nearby building structures. And the other results I'm showing here are for the amplified Nankai scenario cases. The model does fairly better for this case, as it captures the 2 main waves of inundation arriving on land. The issue, however, might be the draining process after both waves arriving on land. The result indicates that in the model, the water does not recede quickly as it is expected, perhaps something to do with the bottom friction. Overall, the subgrid model has generated some encouraging results, but the performance of the model needs to be further evaluated by comparing the results with some other commonly used tsunami and storm surge models, both high resolution and low resolution. And the other possibilities, we can also compare these results with a RAM that does not use any subgrid. And so far, we have found that the subgrid model does not require a large amount of time and computational resources to calculate the inundation. The model does not require large parallel computing systems, and instead it runs on a single computational core and does not take over 1 day after grid averaging. But we also notice that the current limitation of the model is that within a complicated topography, the model tends to overpredict the inundation, probably because the effect of drag by those urban structures located closely together cannot be fully modeled after the averaging process. Also, there is possible error between the LIDAR scanning and the actual topography, which may impact the model results, as some of the smaller structures in the city model could not be captured entirely in the scanning. Our ongoing study aims at improving the model accuracy in the area of high building density, possibly by applying varying bottom friction conditions at those areas. We are also comparing our model results with other common tsunami and storm surge models, such as the Tsunami N2 developed by the Tohoku University and currently used by our colleagues in Kyoto University, and the stock ML models currently used by our colleagues in the PARI, the Port and Airport Research Institute, and they are also run on the same experimental setting. Through the comparison, we may know better how our models performs both in accuracy and efficiency. That's all of my presentation. Thank you very much for attending and listening to my talk. If you have any comments or questions for my study, please feel free to send me an email. I also believe my contact information can be found on the conference website. And thank you very much.